Hey guys, welcome. Today I'm going to be talking a little bit about rate mechanisms and how we can use rate mechanisms not only to understand concepts about how a reaction works, but also to look at rate mechanisms to determine what the rate law of certain reactions are, and use that to sort of figure out how does our reaction rely on its components in order to proceed. So we've talked about within a reaction you have certain rate laws that relate certain of the reactants to the speed of the reaction. It's a mouthful. But what these actually tell you is looks at a method that the reaction undergoes in order to figure out does this mechanism, what they call it, does this mechanism support what we're looking at in terms of how we can see the data. And so I'm just going to go right into it here. Let me switch to this. There we go. Perfect. Alright, so here's my little intro. Rate mechanisms. I want you guys to, first off, we're going to go over a little bit of the concepts, and we're going to determine some rate equations from a very simple basic equation. So when we first start thinking about these rate mechanisms, let's just pull up what a rate mechanism would be. So here you can see a very general reaction. We have NO2 combining with CO, becoming NO and CO2. These are all in gas form. Not that it particularly matters in this case, but just, bring back the point of put on your phases for everything. So this is a reaction, but it's important to realize that reactions don't always occur in one step. So in the past, you probably have seen all your reactions just being like, boom, reactants become boom, products. But almost all the time, there's a multiple step process that it gets from those reactants to those products. And so here, just as an example, here is one reaction mechanism for this reaction. And so you can see here that we actually have two NO2s combining to form NO and NO3. This NO3 can then react with carbon monoxide to form NO2 and CO2. Now when you first look at this, you'll be like, hey, maybe this is kind of weird because we have these two different steps. How does this work? Well, one thing to always keep in mind when you look at these rate mechanisms is that each step should combine to give the overall reaction. So in other words, if we combine these two reactions, right, so we're going to add them together in this case, we should get out this reaction back. So first things we want to look at is we have a reactant NO2 and a product NO2. Since they're on the opposite sides, we can cancel out one. We can't cancel out this other NO2 because we don't have an extra NO2 over here. And also, this NO3 and this NO3 will cancel out. I believe, I forgot to cancel them out. Well, here, guess what I'm about to do? Fix it live. Boom, NO3, NO3, those guys cancel out. So our two reactants are NO2 and CO. Our two products that aren't canceled out are NO and CO2. And you can see those end up in our overall reaction. And so that's what you can basically see how you can connect a chemical equation to its rate mechanism. So the mechanism should always summarize to give you the equation. Alright, so let's move on. So some important information when we're thinking about these rate laws and rate mechanisms. Here I've just thrown up a very generic rate mechanism. It's a little more complicated than you would probably think of. It's a four-step mechanism, which is not too crazy. You would definitely see could see similar things to this in typical chemical reactions. So the question becomes, what is the reaction for this rate mechanism? Now, I've done here, let's see, let's just start to cancel out what we have on both sides like we did in the last one. So it appears D is on both sides. It's both over on the right and on the left, so we can cancel it out. F, I believe, yeah, F is also on the right and on the left, so we can cancel them out. H is also on the right and the left. It's both a product and a reactant, so we can cancel it out. And so we end up left, we have one A here, we have one B here, we have two C's, a C and a C, and we have a G on the reactant side, so those end up here. And then on the product side, we have an E and we have an I. So you can see that this crazy reaction mechanism, it has a lot going for it, only produces 2 actual products, and it consumes 4 total reactants. It's kind of crazy that you get that out of it. So let's think. Well, there's some definitions that we should know when we're looking at this. So we already kind of know 2 of them, and I want to make sure the third one sticks home. So first off, when we're talking about reactants, what are reactants in this mechanism? Well, a reactant is anything that is only a reactant. So here you can see it only is what we're starting with. We start with an A, a B, we start with 2 C's, and we start with a G. And they're used up in the reaction. They don't appear anywhere else in the reaction. They're only on the reactant side. So therefore, those are going to be our reactants right there. Now, we also need to label our products. That one's pretty easy. So if we think about our products, we're going to have, it's the only thing that lie on the product side of the reaction. So here on the product side, we have E and I. Here we can find them both, E and I, right there. So those are going to be our products, right? Pretty simple. And then lastly, there's one new sort of thought we have to look at, and that's what's our intermediates. So when we think about intermediates, this is a chemical that is both produced and used up within our reaction. And so that will be anything that is canceled out on both sides. So it will not show up, in most cases, it will not show up in your reaction, your chemical reaction. It will not show up in the equation. So here we'll find that's going to be D, because it is both produced in the first step and used up in the second step. F, which is produced here in the second step but used up in the third step. And finally H, which is produced in the third step but used up in the fourth step. And you'll see here that I've handily labeled them D, F, and H. So that is our intermediates. And the important thing to notice about the difference between the two is we can control the amounts of A, B, C, and G that we put in to get us to these products. But anytime we have these intermediates, they're going to react to form these products. We're not going to be able to necessarily control them in terms of the reaction. So if we would normally run this reaction, we'd put some A in, we'd put some B in, we'd put some C in, and we'd put some G in, and they would react and you'd get out E and I. You wouldn't put in like whatever reactant D is or F is or H is, because you're not concerned with that part. You're only concerned with the overall reaction equation. So that's why in the future, when I explain this next portion, why we'll have to look not necessarily at intermediates but work our way back to reactants, because that's what we really care about when we're doing these chemical equations. Alright, so what do these rate mechanisms actually tell us? They can really tell us the rate law. So you probably have looked at a lot of rate laws and determined rate laws from data. So you can, use linear plots in order to find the rate law, what order you have, and stuff like that. But another way to look at it is not only can you take that data and find rate mechanisms, you can take rate mechanisms and find rate laws. So we can go back and forth. So let's look at this rate mechanism here. So we have A and B going reversibly. So C can be formed, and we can also have the reverse reaction here of C becoming A and B. I didn't have a good double-sided arrow. This is the best one I could find. I apologize. So actually on this backwards reaction, just to make it clear, on the backwards reaction of it going that direction, we would have a K -1. And here, for the second step, we would also have a K -2. So essentially we have this forward reaction, and we also have a backwards reaction. Here we have C and D combining to form E. There's a forward K2 reaction. There's an E going backwards to form C and D. This occurs at the rate C -2. Finally, we have E going to F at a rate of K3. So, there we go. So if we're thinking about this, the rate law is always determined by the slowest step in this reaction. Now, you won't necessarily be told what the you won't know what the slowest step is off the top of your head. You won't look at this and be like, well, obviously number 2 is the slowest step. You won't know that. You'll have to be told that. So here you can say, what if the first step is slow? So here, what if A plus B forming C is the slow step? That means that this step would be our rate determining step. In other words, our rate is going to be based off of the concentrations of A and B. So in this case, this is actually a very simple problem because the rate is only based off of these two things. So we can say that here, that the rate of this overall reaction is just going to be equal to K1, because that's the rate of our forward reaction, times the concentration of A times the concentration of B. So that's as simple as it is for if it's the first step. Oftentimes when you do a rate law from a mechanism, it'll be super simple to figure out the rate law because if the first step is slow, because there's no need to replace anything. One thing I want to make obvious is, let's throw out a blue here. Let's say that there's a number, let's say there's a 4 in front of that A. It's 4A, then you would need to put that exponent there. If there's a 3 in front of B, you'd have to make sure and put the 3 there, because that will affect your rate mechanism. It affects your rate law directly. So here we're going to have to make sure you keep those coefficients as exponents like you've learned about before. So that's the simple case. Let's think about a little bit of a harder problem. So what if the second step is slow? Then we get a lot more complicated. It's actually not too hard to write down our initial thought, because if our second step is slow, the rate is still found the same way. Let's say our rate then is going to be equal to, so in our first step here, I keep wanting to point at the screen. It's not going to help you if I do that. So follow my red dot. You can see it here. So K2 here, this reaction is our slow step. So our rate is going to be based off of the forward reaction here. K2, so it's based off of K2, it curved that for me, times our concentration of C times our concentration of D. Now, you may think, awesome, that's super simple, but the issue becomes, well, looking at this, D is a reactant, right? So, if D is a reactant, but what is C? Well, C, if you'll notice, is both a product in 1, and it's also a reactant in 2, which makes C an intermediate. Since C is an intermediate, we cannot have it in the rate law. It needs to be replaced by something else. So the best way to get rid of it in this case, since our first step is at equilibrium, since we have a flow forward and a flow backward, they're at equilibrium. So what we can do is use something called the pre-equilibrium approximation or estimation, depending on who you talk to. And so essentially for that, what we can say is, since the second step is slow, every step before that, which is only step 1, has to be in equilibrium. So what we can say by that is that the rate forward, so what's the rate forward for step 1? It's K1 times A times B, that's our rate forward, has to be equal to, since it's at equilibrium, to the rate backwards. So our rate backwards is going to be K -1 times the concentration of C. Now, since we have this information, because we've used the pre-equilibrium approximation, we can solve for C here using this equation here. We can solve for this, for C, and plug it in, and we should end up with only reactants. Now, let's solve for C. The easiest thing to do, I think, would be dividing everything by K -1. Let's go ahead and solve for C here. C, I'm just going to switch sides so it's easier. So these will cancel out on this side, but it's still on this side. That's terribly done. Just remember that we're dividing both sides separately. I wonder if I have an eraser. I do. Perfect. let's write this a little better so you guys can see it very handily. I'm going to divide this side by k negative 1. Means you have to divide the other side by k negative 1. Here they cancel out. Here they don't. So we end up with k1 over k negative 1 all times a times b. So let's go ahead and plug that into our rate law here, and I'll bust out a different color. Let's bust out the red. So let's substitute in for C what we know now. So therefore our rate is going to be equal to a whole lot. Rate is going to be equal to, let's see, K2, and then we have times K1 on top, divided by, looks like K negative 1 on bottom. Now our concentrations that are in this reaction are going to be A times B. Finally, so that's everything's been subbed in for C. We still have this concentration of D left over. Now let's see, are we done? We're not sure yet. We have to check. So this is all just a rate constant. That's fine. A is a reactant because it's not on the products of any reaction, any step of the reaction, I should say. B is also a reactant. Perfect. And D we already knew was a reactant. So, therefore, this is our finished rate law. You can shorthand it to this. You can just change all these to 1K times A, B, and D. So this is just a shorthand because since we can't measure step 1, really the overall rate of the reaction is just going to be based on some overall rate constant K. You don't really need to separate them in this case. In more advanced courses you probably would, and you'd want to keep that there, and if you're asked you should be able to tell, like, oh, my rate constant would have been equal to these values, but I just substituted in and put just 1K because it's simpler that way. You should still know that these are the same. These are equal in this case. Okay, so that's a little more complicated. There's still one more, yet more complicated case. So let's go ahead and move on to the last case here. So again, we have the same reaction, and the rate law is still and always determined by the slowest step. But what if the third step is our slow step? Well, what does that mean? Well, that means our rate is going to be based off of this guy here. So let's just write, what do you think the rate law would be? Well, in this case, it's pretty simple. Our rate is just going to be equal to, let's see, it's based off of this rate constant, so K3, and it's the concentration of the reactants. There's only one, K3 times the concentration of E. Perfect. Well, that was easy, except for, of course, we have the same issue as we did last time, that E is not a reactant. It is instead a intermediate, because we have E over here as a product, and we also have it here. So if we wrote the overall reaction, they would cancel out. So the issue becomes now that we have to get that out of our rate law. So we're going to do the same thing we did last time. Let's keep using green. I'm going to use the same thing we did last time, except for now, since we're at step 3, we can assume that every step before 3 is in equilibrium. So in that case, step 2 is now in equilibrium. So let's go ahead and use that to our advantage. That means that the forward rate of 2 is also equal to the backward rate of step 2. So let's go ahead and write the forward rate, set it equal to the backward rate. The forward rate in this case would be equal to K2 times our concentration of C times our concentration of D. Alright? Our backwards reaction is going to be this way, that way. That's going to be equal to K negative 2, there we go, times our concentration of E. Perfect. Well, let's do the exact same thing we did last time and solve for E and then substitute it in. So solving for E, it's as simple as dividing both sides by, here, I forgot to put the equals, k negative 2, right? K inverse there. So it looks like this k and this k cancel. They don't cancel on this side. So we end up with E equaling to k2 over k inverse 2, k negative 2. And our concentrations are still both there. So we have times the concentrations of C times the concentration of D. Awesome. We have E equal to something. So let's go ahead and just plug that right into our rate law. So our rate then is going to be equal to K3. And then now we're at E, so we have to substitute it in. So let's put it on our K's first. So K3 times K2, and that's divided by K negative 2. Now let's go ahead and put in these concentrations, and we have the concentration of C, and my bracket didn't work there, but that's alright, times the concentration of D. Awesome. So we've gotten a little bit closer, but we're not yet done, because again, the next issue is, now that we're here, this guy, C, it's again an intermediate. So we can't use it for this reaction. Now, for this rate law, sorry. Now, fortunately, since step 3 is the slow step, that means every step before that's in equilibrium, as long as it has a double arrow, which these do. So therefore, we can assume that step 1 is in equilibrium. We can set the forward reaction of step 1 equal to the backward reaction of step 1 and solve for C. Now we already did that in the past, and so just to bring it back up, we know from doing this last time, we know that C equals K1 over K negative 1 times A times B. And so that was done on the last slide. It's the same setup and everything. So once we have C, we can plug it in, and hopefully we'll end up with our rate law. So let's go ahead and go back to red, and let's sub this guy in there. So doing this, we'll end up with the rate of this reaction. It's going to be equal to, let's put in all the K's. So let's put in our ones we had first. We had K3 times K2. Let's see, now K1 is on top as well. K1, all this divided by, we have K negative 2 times, and then now we have a new K negative 1 that we have to worry about. K negative 1. And now let's put in those concentrations. So this substitution gives us A, concentration of A. We get the concentrations of B, of course, from that as well. And then we still have the concentration of D. So, let's see. Are we done? I think we're pretty much done, because A, B, and D are all reactants, so we have no intermediates. We don't have any products or anything weird based off of our rate law. It looks good. Looks like we have a finished rate law. The last thing I would do is just change all these rate constants just to 1 over all K times A, B, D, and there you go. There's our rate law for this step. One thing you might ask yourself when you look at this, you might be like, well, that's weird. That looks like the exact same rate law as if the second step was slow. That's actually true. It is the same rate law in terms of that, but keep in mind now that our K's aren't the same. So though we substitute in this K here, this guy right there, though we make that substitution, keep in mind that it's equal to a whole different set of rate constants. So since this is essentially equal to that, and we don't have to worry about that right now, but that's how you could get maybe two very similar rate equations for two different steps that we're rate determining. Alright guys, so one last thing I want you to keep in mind is that though whatever reaction you're looking at may not be these exact steps, it might not be A, B, C, D, and E, and F. It might be, you know, hydrochloric acid. It might be copper compounds. It might be all sorts of crazy chemicals. The process here is still the same. So if you get confused by the chemistry, just break it down to its most simple elements, A's and B's and C's. Because no matter what you're looking at, you should be able to find what's a reactant, what's an intermediate, what's a product. You should be able to take those, figure out what step is rate limiting, rate determining, so it's the slowest step, and then just figure out your rate law from that, and you can plug in the chemicals after that. It's not like you have to worry about all these chemical reactions occurring while you're trying to figure out the rate law. Once you have the rate law, you can sub in, let's say let's pretend you made this guy copper and this guy nitrates, and you just have these weird reactions going on, and so you can plug in these chemicals later. It doesn't change the way all these setups occur. It doesn't change the way you'll go about fixing them. So I hope this helped you guys a little bit, and if you have any questions or any comments, feel free to leave me information here or email me if you have access to that. Alright, thank you guys. Have a glorious day. Bye.